tug-of-war can be a lot of fun, one group pulling against another. And in the last programme, we talked about how push and pull relates to structures. For instance, gravity tries to pull a building down, and other loads, like snow on the roof, try to make it cave in, and the structure just pushes back against it. But how does a structure know how much to push back by? I mean, it always pushes back by just enough, but not so much that it topples over in the other direction. Well, the answer is that everything a building is made of has a property that we call elasticity. In other words, every material has give and take. That is, it can be squashed or stretched and still come back to its original shape within limits. And that applies to every material. Even stone is elastic. Look what happens when I drop this one. It bounces. That's because it's elastic. It's as if all the atoms are held together or apart by tiny springs that are either squashed or stretched by the forces resulting from the loads. So when anything is loaded, it places forces on the structure that are resisted by the elastic properties of the material itself. The more the load, the more it deforms elastically. In fact, by just enough. Well, that's a bit general, I must admit. So let's look in more detail at the effects of these forces and see what else they do to a structure. Well, there are 5 forces, really: compression, tension, shear, torsion, and bending or deflection. And we shall soon see that they can all be understood in terms of the first 2 fundamental forces of compression and tension. And what's even more interesting, tension is the opposite to compression. Tension is pulling, compression is pushing. Well, that all sounds pretty easy, but there is more to it than that. So let's start with compression. Compression is the tendency to condense material, to squash it. This stone wall illustrates the point perfectly. Look, the top stone is pushing on the one below. These 2 are pushing down on the 3rd one down, those 3 onto the 4th, and so on down the wall. So the stones at the bottom of the wall are taking the weight of all the ones above. The same thing happens to columns, of course, as well as walls. But the key point is this: each stone is pushing on the ones below. Now that's compression. Incidentally, a 2-storey house will shrink vertically by about 3 millimetres or 1/8 of an inch because the bricks compress elastically under their own weight. In fact, all buildings will shrink a little under their own weight. The taller they are, the more that will be. About 50 millimetres or 2 inches for this 30-storey apartment tower. Now, tension is the tendency to stretch material, to pull it apart, the opposite to compression. Nature has given us some marvellous examples of tension in structures. The spider's web is perhaps the best known. It's pure tension. As for man-made examples, well, look at this rope bridge. It's a simple form of the suspension bridge. There may well be examples of bridges in tension in your own area. Here's a building that uses tension, the West Coast Transmission Building in Vancouver. The floors actually hang from the cables, which themselves hang from the elevator and stair tower. Let me demonstrate how tension and compression can work to achieve the same result, namely to keep a structure up. I've taken this ball and I've supported it by hanging it from a piece of string. That's tension. But I could also take it and put a prop of some sort underneath. That's compression. Now, it's easy to see that by hanging the ball, we can get a structure that is much lighter. And that can be very important. Remember, the dead load, that is the weight of the structure itself, can be the most significant load. And usually we want to make that as light as possible. So in general, it's almost always better to use a structure in tension, because that will always result in a structure that weighs the least. But there is a penalty to pay. You don't get something for nothing. A structure in tension is not as stable. It will blow about in the wind much more easily, for instance, than a structure in compression. So, a structure in tension is affected by live loads in a much more demonstrable way. You see, you can blow the spider's web and it moves. A blade of grass can bend in the wind, and when the wind stops, it comes up straight again. But we don't want our buildings to do that. That's a bit hairy. And although they do sway, of course, within limits, we don't want this movement to exceed the point of safety or even discomfort. Remarkably, the CN Tower in Toronto, the tallest freestanding structure in the world, will sway 3 feet, nearly a metre in a hurricane, perfectly safely. So compression is pushing and tension is pulling. Another effect of loads on a structure is called shear. Shear is sliding. It's the action of dividing a material along a very thin plane that's parallel to the opposite forces. Now, what on earth do I mean by that? Well, it's really the basis of the cutting action of a pair of scissors. Look at this pair of metal cutters. If I open them, there are the 2 blades, of course, and I can run my finger along them and nothing happens. They're not sharp at all. But I can cut this piece of metal and I can cut this piece of paper. So how come they're not sharp enough to cut my finger, but can cut through paper? Well, it's not sharpness per se that's the important thing. It's really how closely the 2 edges of the blades are touching. The closer they are together, the better they can shear something. Let's take an expanded view of what's happening as the edges of the 2 blades come together. When we blow up the picture, you can see that the 2 cutting edges are pushing against the 2 sides of a rectangle. They distort that rectangle into a shape we call a parallelogram. Look at what's happening to the material within that parallelogram. Let's just draw in the 2 diagonals from corner to corner. There. When the form was a rectangle, before we started to close our shears, both of the diagonals were the same length. But now, as the shears close and the shape becomes a parallelogram, one of the diagonals shortens. That's compression. And the other lengthens. That means tension in the material. So in fact, when we use the shears, we put the material under both tension and compression. They are acting at close to right angles to one another in the material and as much as 45 degrees to the cutting action of the shears. And believe it or not, that is why the paper or the metal sheet is cut. What does this have to do with buildings? Well, shear is the force on these rivets as the 2 sides try and move in opposite directions. This is a time when shear works against us. It sets up the same pattern of tension and compression inside the rivet that we saw when we cut the metal with the shears. So we fight it by making the rivet so tight that the rectangle becomes very, very small and the rivet can't shear. Our next example of a force from loads is called torsion or torque. For instance, every time we turn one end of a rod and the other end isn't free to turn immediately, we twist it, and that's torsion. Let's look at this in more detail. I happen to have a cylinder of material that twists quite easily, and I've drawn a grid on it so that we can see what happens when I twist it. Now, the lines along the cylinder are straight, and the ones at right angles round it are circles. That's formed sort of curved squares, because they're not on a flat surface, they're on the curved surface of the cylinder. Now, I've clamped one end of it, so let's twist it and see what happens. There. Nothing much has happened to the circles, but the long lines are no longer straight. They're curving spirally around the cylinder. That means, of course, that the squares have become parallelograms. Now, that means we have tension in this direction and compression in that direction, just as we had with shear. And like shear, torsion could cause a cylinder to break along either the spiral path of compression or the spiral path of tension. Here's a good example. Here's a piece of chalk, and if I twist and break it, it does so along a spiral path. With a wet swimsuit, we have a simple example of using torsion to our advantage. When we twist it, the water squirts out. It's the compression caused by the twisting that pushes out the water. Now, this principle has had a revolutionary effect on the world of fashion, the clothes we wear. The revolution occurred in Paris in the 1920s. The leader was a designer named Mademoiselle Vionnet. But our story starts way back with the Victorian corset.
This is a Victorian corset right here. This one has aluminum rods in it. Back then, however, they would have used wood or whalebone, which are actually much more rigid and form your bones inside so that you'll get that shape.
Now, in Victorian times, the whalebone corset pulled women into tiny, slim-waisted shapes by applying extraordinary forces on their bodies, as we see in this demonstration at the Ontario Science Centre. The clothes were fitted to an almost rigid frame, and they always looked perfect. But the poor person wearing them had to suffer considerable discomfort, even to the point of affecting their physical health.
Now, you have to keep one thing in mind. This is a very, very large corset. It's much larger than anything they would have worn back in the Victorian period. It's made to fit people who work here at the Science Centre. Back then, they wanted very, very tiny waists, much smaller than we have today. And in fact, to be considered fashionable, the average woman was expected to have a waist size of about 43 centimeters or 17 inches. If you want to know how large that is, just put your hands around your neck, and that'll give you a basic idea right there.
Fortunately, women were liberated from the corset in the early part of this century, after the end of the First World War. The result was a lot of freedom in fashion, but also a lot of seemingly shapeless, ill-fitting clothes for women. They just sort of hung there. And that was really due to the way the fabric was woven and cut. The warp and weft of the weaving, the cloth of a dress or a blouse or any garment, was subject to tension, just because of its own weight. I know that seems unlikely, so let's see for ourselves. Now, in the cloth, the weft goes in that direction and the warp goes in this direction. Or is it the other way round? Well, it doesn't matter really, because what happens is that in tension, gravity, or you pulling down on the cloth, makes the long fibres get longer, and the ones in between, well, if anything, they sort of pinch together and get saggy. And that's what used to happen to clothes, and it still does. That's why you get baggy dresses, baggy knees, baggy everything else. Well, in 1922, Mademoiselle Vionnet invented what she called the bias cut. She figured that there was a way to get a clinging fit other than pulling strings on corsets and things. She found that if she put the cloth with the waft going in this direction and the warp going in that direction and pulled down, then both sets of fibres got longer and clung. The easiest thing is for me to demonstrate on my assistant here. Now, if I draw a grid on the bias, like that, and then pull down on the cloth, then there's a tendency for this grid to distort into a diamond or parallelogram shape that we've seen before. Oh, it's true that there is compression across there, but if the cloth is cut on the bias, there aren't any stringy bits of cloth in between to sag. So, although there's lateral compression and longitudinal tension, the result is that the fibres at an angle work together to give a much more satisfactory clinging sweater sort of look. Thank you. Of course, had we stopped to look at the world around us a little more closely, we would have seen the same principles at work in one of the world's true survivors, the shark. It's not built like other fish. It doesn't have a hard, bony skeleton. Some people regard it as more primitive than that. Well, the problem is that without a skeleton or a corset to hold its shape, the shark would be in great danger of kinking when it swims. It twists and bends as it swims, but oddly enough, it doesn't kink. That, of course, is dead lucky for the shark and its digestion. So why doesn't it get dents and kinks as it moves about? We can find the answer in its unusual skin. It is, in fact, structured like a bias-cut sweater. But how does this work to prevent kinking, when in a sweater it works to make it cling better? what's the relationship? Well, let's have a look at two different kinds of tube for the answer. This one has the grid on it that we've used before, whereas this one has a double spiral pattern. Now, when we bend this, the inside of the curve is compressed, and that means that the lines along the tube try to get shorter. They can't, of course, so they kink up, just like the material does in a baggy dress or sweater. But look what happens with the other. This time, the compression on the inside of the curve forces the intersections of the lines closer together, but there's space between the material for it to squeeze into. So such a tube can be turned around quite tight curves without kinking. Of course, there is a limit. Eventually, those on the inside would pile up on each other, and on the outside, they would be stretched too far, but nowhere near as quickly as they would with this one. In our own world, we have also learnt to use what the shark has had for millions of years. This is a common garden hose. It too has helical bands to hold it both together and apart. This hose, just like the shark, has a great resistance to kinking as we bend it around the obstacles in our gardens. That means it never constricts the flow of water inside. Any hose that is not built that way, in fact, will kink. And you can stop the flow of water, which is quite a nuisance for us. Of course, it would be a blooming disaster for the shark. The cat's pyjamas in this warp and weft business is the solid fuel rocket, such as the boosters used for the shuttle.
1 and liftoff. Liftoff of Discovery and the first flight to retrieve and return satellites from space.
Now, designing the outside casing for such a rocket is not easy. It has to withstand considerable forces as the fuel burns. A solid fuel rocket has, of course, a cylinder of solid fuel inside, and actually there's a hole drilled up the middle to help it burn to the top. It's ignited in the centre, but the fuel burns so fast that it cracks almost immediately because of the thermal shock on the fuel, just like putting boiling hot water inside a cold drinking glass. The rocket fuel burns along the cracks, nipping almost immediately to the outside casing. Well, the rocket casing is made of metal and gets hot very quickly. It wants to expand, and the only way it can do so is to make its diameter larger. But that, unfortunately, makes it too big for the plug of fuel. The result? The fuel falls out of the bottom of the rocket, to the immense embarrassment of everyone concerned. So the problem the designers faced was how to stop the sudden expansion of the diameter of the rocket casing, and the only way to do that was to bind it helically around the outside with something that would not be subjected to conduction and expansion, or at least not as rapidly. It had to hold long enough for the fuel to burn further up the rocket, and it worked. Winding the warp and weft tightly at just the right angle meant that the only way for the casing to expand was along its length. Today, many big solid fuel rockets use this method in their construction. It's just another example of Mademoiselle Vionet's bias cut. Well, she died at the beautiful age of 98, blissfully unaware of her contribution to space travel. And of course, all explainable in terms of compression and tension and the control of torsion or twist. So now we come to bending. At first sight, it's not so much a force as it is a phenomenon, both vertically and horizontally. And it's the result of tension and compression, as we'll see in a moment. We see bending in nature when it is essential for a structure to withstand loads from almost any direction. Let's look at a blade of grass. If the wind blows, it bends. That means that the front side is compressed and the back side is stretched or in tension. So even a simple blade of grass has to be designed to contend with that. Well, what is even more interesting is that the grass never knows which way the wind is going to come from. So it has to be able to resist that all the way around it. That is why the cross-sections of grasses and twigs are so beautifully symmetrical. It's the only possible response to the vagaries of nature. In the man-made world, the best vertical columns are circular ones. The only problems they have is that it is difficult to fix things to them. That's why we often use compromise verticalised sections, like the simple square post that holds up a stop or parking sign. For horizontal members, the situation is a bit different. In general, the bending is only going to be in one direction, down. So we find that the ideal shape for a beam is not circular, but rather rectangular or eye-shaped. Mind you, bending is not necessarily bad news. Lots of things can bend and not break. But a problem comes when we connect things that can bend with things that don't like to bend, such as windows and plaster. They crack. So really, bending or deflection is more of a nuisance to us rather than a problem.
There is a product of bending that does produce additional forces. It's called bending moment, and it's the simple action of the lever arm. We see it best in the action of the teeter-totter or seesaw. Here you can see that even I could be tipped in the air by somebody much lighter than I am if I sit closer to the pivot. It would vary, of course, for different combinations of people, and it doesn't take long to figure out that there's a relationship between the weight of the person and the distance they are from the centre.
And the formula is very simple. You just multiply the weight by the distance from the pivot for both sides. If the answer's the same, you balance. If one is bigger, that's the side that goes down. So the greater the distance the weight is from the fulcrum, the greater the force it can exert.
And if we don't take that into account when we design our structures, the consequences can be surprising, to say the least.
Let's look at kitchen cupboards. If the designer has made a mistake or been careless, you might have a set of drawers right next to the hinged side of a cupboard door like this. If the drawer is accidentally left open a little, the door comes around like this. And if you push on the door, you can put half a ton on that hinge and break it with little effort on your part, just because you've left the drawer open a bit. You see the same thing in the drop-down flap on some desks. If it sticks out too far and you lean on it, you can snap it right off. And all because of the phenomenon of bending moments that we demonstrated with the teeter-totter. Now, I can guess what you're saying. We don't usually build teeter-totters into our buildings. Well, just look at these illustrations. Here we see a teeter-totter being held up by a strong man that is bending under the weight of the two people on the ends. Now look at what happens if we invert the drawing. Our teeter-totter has become a beam with our heavyweight champ doing a handstand in the middle. If we move him closer to one end or the other, we increase the load on the person holding up that end. He would have to be stronger to keep his end up. An example of this phenomenon can be seen in this parking garage. The cars move, which results in the columns being loaded differently at different times. Not only that, the cars might be parked all at one end while the other end is empty or unloaded. So the columns have to be designed to contend with the worst situation. But there are limits to strength. The force on the structure, whether it's compression or tension, produces stress. The stress is the intensity of the force on every unit of area. The larger the force, the greater the stress can be. The structure responds by changing its shape a bit, by deforming. That's part of being elastic. And we call the actual amount of deformation the strain on the structure. The greater the stress, the larger the strain. Now, there are limits to both. Even elastic materials can't deform endlessly. An elastic band will snap if the stress and strain are too great. A ruler will break, as a rule, that is.
So, every structure we design has to take bending moments into account. For instance, with this aircraft, too much load on the end of the wing and it could break. On the ground, it's the fuselage that's holding up the wing. But interestingly enough, when the aircraft is in the air, the situation is reversed, and it's the wing that's holding up the fuselage. Now, this is important because sometimes what was in tension on the ground could become compression in the air. So, too much stress of the wrong sort on any structure could cause it to fall apart unless it's been designed to take it. To review then, the forces of shear, torsion and bending are really just expressions of compression and tension. And it is compression and tension, push and pull, that governs so much of our world. Without being aware of their effects, we'd have a hard time designing a structure that would stand up, let alone fly. In the next programme, we shall begin to look at the design of some of these structures. Home, James.
It's a heck of a day for this one, Brian.
British way.
Oh, you're right.
Okay, what we're going to do is just taxi up here. Now